This is your classic. An experiment is conducted to calculate the velocity at which Mitchell can hit a ball. A tennis ball, mass 57 grams, hits horizontally into a ball of clay suspended by a string. The ball of clay has a mass of 500 grams. When the tennis ball hits the clay at x, it becomes embedded in the clay. That's your collision. And then the combination of the clay and the tennis ball rise up to a point 1,04 meters above the original and assume air resistance is negligible. State the principle of conservation of mechanical energy, that your mechanical energy in an isolated system remains constant. And you could have said something about mechanical energy being kinetic plus potential. Using energy considerations only, show that the speed of the tennis ball and clay at point x is 4,5 meters per second. So we need to start by saying kinetic energy at the bottom is equal to the potential energy at the top. Now the good news, a half mv squared is a half, no isn't, it's mgh. Cancel out the m, so we don't really care about the mass of anything in this. And we've got half of the velocity squared is equal to 9,8 multiplied by a height of 1,04. And I find that the velocity does turn out indeed to be 4,5 meters per second. And it was a speed, it wasn't a velocity, so we don't need a direction. Calculate the initial speed of the tennis ball immediately before the collision in kilometers per hour. So now we're interested in the collision, so we need to say that momentum before the collision is equal to momentum after the collision. And before the collision we have got a 0,057 kilogram ball approaching at a velocity that you don't know, plus this whole system over here is stationary. Afterwards, these two added together is 557 grams, so the mass is 0,557 multiplied by the new velocity, which we've just worked out to be 4,5, since they stuck together. When I resolve that, I find that my velocity turns out to be 43,97 meters per second. So it was important to convert it into kilograms each time, and we've got meters per second, but that's not the question. The question wants us to go to kilometers per hour, so I need to take that 43,97 meters per 1 second. 43,97 divided by 1 second is the same as 0,004,397 kilometers. So I divide by 1,000 at the top, and I go 1,300th of an 3,600th of an hour, and when I resolve that I get 158,31 kilometers per hour. Mark has a mass of 94 kilograms on Earth. He goes on a space mission to the moon. On the moon he finds he has a weight of whatever. The mass on the moon is given over there. Calculate the gravitational acceleration on the moon. So we know that force gravitational is always equal to mass times gravitational acceleration. We're told what his force gravitational is on the moon, which is called his weight. We know his mass is 94, and therefore we can work out the gravitational acceleration on the moon is equal to 1,68. And again, they don't say the magnitude, they just say gravitational acceleration. So meters per second squared downwards does have a direction associated with it. Using the g that you've just determined, calculate the radius of the moon. So we know there's an equation that goes g is equal to gm over r squared. So we know it's 1,68. We know this g value is 6,67 times 10 to the negative 11. Sorry, this is smushing. And we have a mass of the moon, which is 7,4 times 10 to the 22. And then that is all over r squared. And then when you invert and square root, you find that r is going to turn out to be 1,71 times 10 to the 6, and don't forget units, meters. State Newton's universal law of gravitation. You can't write this down, but any two objects in the universe attract each other as a force, with a force. That force is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. And you need to write that all out in words, but that equation in essence summarizes it. In a NASA display case, two identical silver-covered balls are suspended by thin insulated threads as shown in the diagram alongside. Each ball has a mass of 4 kilograms. They are mounted so that their centers are exactly 1 meter apart from each other. What is the gravitational force of attraction between these two balls? So Fg is equal to, we've got the equation up there, substituting in 6,67 times 10 to the negative 11 multiplied by their masses and divided by 1 squared, and I land up with 1,07 times 10 to the negative 9 newtons. So that would be the attraction due to gravity. What charge of equal magnitude should be placed on each ball so that the electrostatic force of repulsion would exactly balance out the gravitational force? So now I take that gravitational force that we have just calculated and I now make it an equal electrostatic force. So electrostatic force is equal to K Q1 Q2 over R squared, and that is 1,07 times 10 to the negative 9 is equal to, and my K value is 9 times 10 to the positive 9, and then I don't know the charge, but it's Q squared, not 2Q, it's Q times Q, and then you've got a 1 squared down there. Rearrange and square root, and you find that the charge on each one is going to be 3,44 times 10 to the negative 10 coulombs. And finally, we are asked to determine the magnitude of the force that a point charge of 3 millicoulombs will experience if it is placed in an electric field of that strength. And so I say force is equal to electric field strength multiplied by charge, 2,500, multiplied by 3 milli, so it's 3 times 10 to the negative 3, or 3 divided by 1,000, 0,003, and I land up with 7,5 newtons.